Good morning, learners. It is my privilege to spend the next hour with you, trying to maybe give some structure to your mind regarding the physics, especially we are going to discuss topics for physical science paper 1, the physics. So I really want to remind you about the important principles on each topic. And the important principles that are going to be tested in the next exam, and maybe also to remind you to watch out for some common errors that often occurs often occurs in previous papers. So, like in the paper, at first you start off with the question 1. And that is normally the multiple choice questions, and maybe at the later stage I will just also refer to maybe how to handle your multiple choice questions. But at this stage I'm going to start off with your normal topic of question 2, and that is about Newton's laws. I'm going to first start off with Newton's first and second law. Now remember, you can have a look at each paper. One of Newton's laws will be asked from you to define one of Newton's laws. That is a fact, so make sure that you know Newton's laws. Let us then start off with Newton's first law. And in Newton's first law, it is very important that in his first law, there's a state which you start off with, a state. And that state is described in 2 ways. Either rest or uniform motion or constant velocity. It's very important. You can't just mention a body in a state of rest and then continues. You must mention both states, rest or uniform motion or motion at constant velocity, because in physics rest and movement at a constant velocity is the same principle. So you must mention both for the first mark. And then unless, very important, that word unless, often that word unless is substituted by another word with a different meaning. So stick to the word unless. And then the second part for your second mark is unless a net force or a resultant force acts on the body. So again, what is a common mistake here? It is very important. You can't just say unless an external force, an external force or a non-zero force acts on the body. Just mentioning an external force or a non-zero force is not correct. It's not acceptable. So please stick to a net force or a resultant force acts on the body. Not just in general an external force. An external force doesn't mean it's a net force. So please stick to the correct words in Newton's first law. And again, it's often asked, so please know it by heart. Then in Newton's second law, you start off with the preamble mentioning that a net force acting on the body will cause acceleration. And the second part is actually the important part, and that is where the marks is. So you must start off, the acceleration is directly proportional to the force and inversely proportional to the mass of the body. So start off, your comparison must start off with the acceleration is directly proportional to the force, inversely proportional to the mass. So very important, that part. You must also somewhere mention the word net force. If you start off with the preamble, when a net force acts on a body, the body will accelerate in the direction of the force applied, but you must mention a net force. When a net force acts on a body, if you don't mention it in the preamble, then at least you must mention it. The acceleration is directly proportional to the net force in the second part. So very important, the word net force also. And then secondly, start off with acceleration and then compare it to the force and the mass. Now, when a free body diagram is asked in such a question like question 2, there's a 90% chance that you will be asked to draw a free body diagram. So just let me just put this diagram on here. Many times the body is on an incline, and then there's forces acting on the incline, in the direction of the incline. In this instance, like I've indicated on the diagram, there's an applied force, FA, and then maybe there's a frictional force, and then there's a weight, and then there's a normal force, and very important, that normal force is perpendicular to the incline. So what I want to ask you, please, if it's an incline, remember your normal force is perpendicular to the incline. And your free body diagram must indicate that FA, the applied force, and the frictional force works at an incline, parallel to the incline. And very important, then your weight is acting downwards to the center of the earth. Now, labels, remember, and I'll come back to it, labels very important. Make sure that you know the correct labels. If you have asked to draw a free body diagram, please don't show the weight, you see this component here, and its components. If ask a free body diagram to draw for marks, only draw the weight component, the weight. Don't indicate the vertical and horizontal components. You will lose a mark for showing both. Later on, for your own rough work, now you can indicate the vertical and horizontal component of the weight, but for marks to be drawn, just stick with the weight. So do not confuse a force acting at an angle with a force acting at an incline. Just here the example. Here is your example of a body moving across a horizontal plane, and now the force is acting on with a certain angle to the horizontal, and now the horizontal component, you will know it is just been calculated by F cos theta, and theta is this angle. That is versus the horizontal component of this incline. The horizontal component of the weight on this incline, you will remember, is Fg, the weight sine theta. So you see on the horizontal plane, where object just moving on a horizontal plane, it is F cos theta, and when you must calculate the horizontal component on an incline, then it is Fg sine of theta. So just remind you of that difference, and be sure if you are working with an incline or just an object moving along a horizontal surface. Right. Then problems on Newton's second law. Now you've maybe been asked to define Newton's second law for 2 marks, and then normally one of the next questions, they're giving you an example of a certain problem, and to help you, they ask you to draw a free body diagram. Now the next question will be to calculate either a tension or acceleration or one of the forces. It's very important now, and I think because it's a grade 11 topic, I think you have enough examples that you have worked through when arriving at the matric final exam. I think you have completed quite a few problems on Newton's second law, applying Newton's second law. Now, Newton's second law in words, let me just go back, okay. In Newton's second law, in symbols, it is F net equals ma. So, somewhere in your calculations, you must show that you start off with F net equals ma. You must show that you apply Newton's second law to solve that specific problem. And immediately there's one mark on showing that you are working with Newton's second law, F net equals ma. And normally, you must solve it with simultaneous equations. So, in other words, you will use that formula for both objects. Right. Now, please, very important. Say, for instance, they don't ask of you to draw a free body diagram of any one of the objects. Still, on your own rough work, you must draw the free body diagrams of all the objects, one or two objects. For your own rough work, you can't complete, or you can't attempt to solve a Newton's second law problem without a free body diagram for both objects, or at least all the objects given in that question. Sometimes it can only be one object, and then it's very important. Why? Because you want to take into account all the forces, and very important, in the direction of the motion into account. So you must take all the forces acting on the body in the direction of the motion. It's very important, and that's a reason. And then you can start substituting for each body into Newton's second law. Right. Now, it's very important that you must realize, if you work with a system of two bodies, maybe moving on an incline, or with a string across a pulley, or whatever, if you use this formula, that A can never be the value of a gravitational acceleration. Please remember, that is the net acceleration of the system, if it's two bodies moving in a system. So that A is related to the net acceleration of the system. You are not allowed in any way ever to substitute the gravitational acceleration. Yes, there's a place for that, maybe when you elaborate on all the forces acting, which causes F net. But, so you are going to use G, the gravitational acceleration, but it is not, this is not the value of G. This is the value of the system and the acceleration, the net acceleration of the system. Very important. And again, now your key definitions in this regard. Now, we have discussed Newton's first and second laws, and that is maybe the two most important laws regarding forces and the movement of a body according to that force, acceleration, or moving at a constant velocity. I'll come back to Newton's third law. First, on Newton's universal gravitational law. Now, that's a very important law, and you will realize that that law have a big influence on our living on this planet Earth. And it's very important that law exists because each object with mass, that law states, each object with mass attracts other body with mass with a force that is directly proportional to the product of the masses. Both objects play a role in that force between the two objects. Therefore, in Newton's gravitational law, it's a product of the masses. Product taking account the mass of the Earth, for example, and your own mass, or any two other masses. So it must be the important word, the product of the masses, and then inversely proportional to the square of the distance. And because you are working normally with big objects, you must use the phrase between their centers. You can't use the phrase the square of the distance between the objects, because the Earth has a massive radius and you can't work from the surface of that object. So very important, in Newton's gravitational law, you must end off and inversely proportional to the square of the distance between their centers. Important words, therefore, the product of the masses and inversely proportional to the distance between their centers. Very important to get 2 marks for that. Then remember, if you have calculations on Newton's universal gravitational law, remember to square that R value. It is inversely proportional to the distance between their centers. So it is 1 over R squared. Very important, in your calculation, remember to square the value of R. Many times learners forget to square that value, and then it is unfortunately you lose 2 marks for a wrong substitution and therefore a wrong answer. You will have seen in the September exam and in previous, many times it's maybe on a multiple choice question where they don't give you specific values. They will relate the problem to if the radius of the planet will double, what will be the influence on the weight of the object. So make sure that you look at multiple choice questions where you don't work with specific values, but with relations between the masses of the two objects and the radius. So they change the mass of one of the objects, or they change that radius between the centers of the two objects, that you are able to work with that non-specific values. So just keep that in mind for Newton's gravitational law. Okay, maybe then moving on to Newton's third law. Newton's third law don't have, in question 2, there's not many applications to be asked on Newton's third law. Mostly that is applied to, later on you will see in question 3, question 4, the conservation of linear momentum. But still, they can ask to define Newton's third law, and I think the important stuff is here that reaction force is opposite directed, and it is equal of equal mass. So if object A exerts a force on object B, object D will simultaneously, it's important, simultaneously exert, and then the important part, opposite directed, but equal in magnitude. So you will, examples of a very simple example of where Newton's third law comes into play is if you place a certain object on the surface of a table, then there's immediately an action-reaction force. The object, the weight, exerts a force on the table, the surface of the table, and then the surface of the table exerts an opposite of equal magnitude force upwards, and normally then we call that force a normal force. So at least be able to identify the action and reaction force. I haven't put it on the slideshow, but it's very important to know that your action and reaction forces acts on two different objects. And Newton's law states this. You will see the action force acts on object B, and then the reaction force is exerted on object A. So the action force reacts on B, and the reaction force is from B on A. So you don't have two forces acting on one object in Newton's third law. It is two forces acting on object A and object B separately. So that is that pair of forces, action and reaction. If you can put Newton's third law in a symbol form, then you can do it by this way. So the force exerted by A is equal to the force exerted by B on A, but very important, the direction of the force exerted by B differs from that, is opposite in direction by the force exerted by B. Now, like I've said, Newton's third law, the conservation of momentum is directly drawn from Newton's third law. They are inseparable, and you can also, by means of equations, derive the principle of conservation of momentum from Newton's third law. If you rewrite Newton's third law, into the statement or the principle of the conservation of linear momentum, you will end up with this formula. And this formula you must really understand, and I'll just remind you, coming to later on to momentum, the very important principle here, and that negative sign is always the problem with learners. They relate the principle of conservation of momentum just by stating the change in the momentum of A equals the change of momentum in object B, and that is wrong. You will see, then you state that Newton's third law state just equal in magnitude the force and not opposite in direction. So be aware, if you want to apply the conservation of momentum by means of this formula, you must realize that the change in the momentum of the object A is negative, the change on B. So in this method, and I don't really advise you to use this method to solve problems on the conservation of momentum, but if you apply it, you must realize this equation states that the change that object A on its own before collision and after collision undergoes is equal in magnitude on the change of momentum that object B undergoes, but very important, it is in opposite direction. Right. This is now on Newton's second law. The first question 2. Let us move now to the next topic, and that is question 3. And question 3, you will see, is also always on vertical projectile motion. So I haven't start off with on the slideshow with mentioning that, but let me do it before we start. Again, here are some definitions. So again, you can't even start off with the topic without knowing the definitions and the laws that must be applied on this topic. And the first definition, like I said, sorry I haven't indicated on the PowerPoint presentation, but the first very important definition is the definition on what is free fall. How can we describe free fall? And it's very, very important that you start off firstly that it is a motion. It is a motion whereby, very important, the only forces acting on that object is the force of gravity, is the gravitational force. The only force acting on an object, while moving, if that is gravitational force, that only force, then you know the object is in free fall. Immediately when another force is present, like friction, applied force, it isn't free fall anymore. So you will see in the past papers quite a few times they have asked you to define what free fall is, and the very crucial part of that, the definition, is the fact that you mention that the only force acting is the force of gravity. Now, then also you will maybe ask, not often, but what the projectile is, and that is a body on which gravitational force acts and then undergoes the movement called a free fall. But you can just go back to your exam guideline and look at that precise definition of free fall. Now, the next question is, all that they can ask you is some scenario given to you, object being thrown from the top of a building, falling down, or if they want to make it more difficult, it is maybe one object thrown from the top of the building and simultaneously a second object is released from the top of a building. What I'm asking you is please to understand the problem, the scenario. Understand the scenario, what precisely is happening. Make sure that all the data given to you is indicated on your diagram on the paper. If they don't indicate on the diagram all the data, please indicate on your own, on the paper, go and write down all the information given on that whole scenario. Because that will help you on deciding which is the most effective formula to calculate what's been asked for you, the final velocity or the time taken. If you have a question on calculate the final velocity for 3 marks, you must know that there must be a method being used by just making use of one formula to solve the problem. So for you to go for 3 or sometimes either 4, starting off with a multi-step calculation for 3 marks, you must know you have started off wrongly. There's a simpler way. You have chosen the wrong formula of equation. So again, go back to your data sheet and look for a question for 3 marks. Identify the correct equation of motion, and please solve it with that specific correct formula. Don't fall to the trap with a multi-step calculation for 3 marks. You just are going to lose marks, and for the unnecessary steps, you're not in any way going to get marks for that. Very important. You know, many of the questions on vertical projectile motions counts 3 marks. So firstly, choose the correct formula. But then secondly, you must make sure that you assign the correct direction signs to a specific quantity. You normally are working with a projectile moving upwards and downwards. So your velocities, initial and final, your displacement, delta y, your gravitational acceleration, that is all vector quantities. So make sure that you choose, say for instance, upwards as positive, and then you award signs to each specific value given for initial velocity or whatever. If you choose upwards as positive, then you will know G, gravitational acceleration, will be negative, and for instance, your initial velocity, throwing it upwards, will be positive. Because it is really heartbreaking to see a learner just by awarding a wrong sign or just omitting a sign ends up with getting 1 out of 3 for a relative easy question because you have awarded the wrong signs or just disregard the signs of the different vectors. So that in your calculations is very important. Remember that your gravitational acceleration is always downwards. Please, if the object is moving upwards or downwards, gravitational acceleration must and can only be downwards. If you're just working with a ball being dropped and the initial velocity, the displacement, etc. everything is downwards, then you will choose downwards as positive, because then all your values is positive and you make it much easier in your calculations. Right. Now, here's just an example. For instance, for awarding signs, so if you have a ball being thrown up in the air and you must do some calculation for the first part, I've indicated here on the example, you can see that I've chosen upwards as positive. Therefore, the initial velocity will be a positive value. Therefore, delta y will also have a positive value. And then because G, although the object is moving object, G will be minus 9,8 because it's always acting downwards on the object. Then just remember rounding off correctly on your final answer. Only on your final answer. Remember, we suggest that you don't round off if it is a multiple step question. If you see that question is worth 5 marks, then you certainly know it must be a multi-step question. Don't round off on too harsh on the first answer of your multiple step question. Either use the answer that you have get on your calculator, use that answer, or at least stick maybe to 3 corrected rounded decimals in your first step. But then your final answer must be correctly rounded to 2 decimals. Examiners take into account the fact in a multi-step question that in your first answer there can be differences that the learners use. Some of them just use a calculator answer, and some have some kind of rounding off in the first step. And therefore, in a final answer, at least there's a range taking that into account. But the principle is, maybe don't round off in the on your first answer, but correctly round it off in your final answer to at least 2 decimals. You can have more than 2 decimals in your final answer. Just make sure that it's correctly rounded. That it is correctly rounded. Okay. And then important, use your data sheet. You have the 4 formulas of equation on your data sheet. Don't get 0 out of 3 because you have by mistake state, for instance, VI equals V final equals VI delta T, and you, for the last part, you forget to square the delta T, half G delta T square. So use your data sheet. Write down the correct formula. Don't even if you think you know it really by heart, just for a final exam, maybe you're a little bit nervous. The data sheet is there. Just look at your data sheet and make sure that you have written down the correct formula. Now maybe just on graphs, on vertical projectile motion. Okay, if you are asked to draw a graph, just make sure that the labels, many a times that the labels are correct. Many a times marks isn't awarded to, say for instance, this velocity or time on your graph, but at least the examiner expects you to at least label your graph, the axis y and x axis correctly. And then normally they ask you to indicate the calculated values or even given values on the graph. So make sure that you, in this instance, the time of 1,22, in this instance, the initial velocity of minus 9,8. So indicate that values asked. And then remember, in a graph, you must also have a chosen direction. And therefore, that will have implication on your graph. And for instance, in this instance, this learner has chosen, I can just get my mouse working, but anyway, there it is. This learner has chosen upwards as positive, so therefore G will be negative. Therefore the gradient of his graph must be a negative gradient because G is downwards and he's chosen upwards as positive. Therefore, say for instance, in this instance, this initial velocity is positive, so he's throwing this ball upwards. This ball B, you can see, has a negative initial velocity, so that indicates that ball is being dropped at time 0. So if you have 2 objects moving, remember that 2 lines must be parallel to each other because both objects are free falling, both objects having an acceleration of minus 9,8. So these 2 gradients must be parallel to each other. If they've just been asked to draw a line of just a single object moving, then the principle is only it must be a straight line for velocity against time, and that straight line must be either have a negative gradient or a positive gradient according to your decision on what your direction is been, the direction you have chosen. Remember then, like I've said, V versus T graphs, velocity versus time graphs for vertical projectile motion, you are working with straight lines with a gradient, positive or negative, and then if there's 2 objects moving, that two straight lines must be parallel because the gravitational acceleration of both must be the same. Right, if they ask you to draw a graph of delta y versus delta t, then you must remember that must always be a curved line. And sometimes to draw a graph of delta y versus delta t, because it's curved lines, it is actually a more difficult graph to draw. So make sure that you've been able to work backwards from a velocity time graph given to a delta y displacement or position versus time graph given. So expose yourself to a few graphs where delta y is drawn against delta t, and that you can relate this to a delta to a velocity time graph. So play around backwards and forwards to draw graphs, the one from the other. Your textbooks have a lot of examples. There's a lot of examples also in previous question papers. So make sure that you've been able to draw a delta y versus t or a v versus t graph. You will see in previous papers, to draw a graph is often one of the questions. So work through a few examples on that. Right, that is now the few principles on a vertical projectile motion. Then moving on to question 4. And question 4 is then normally our topic on momentum and impulse. Now, again, a definition will be asked of you, and the most likely definition to be asked on momentum is the conservation of momentum, because that's the most important principle. And it's very important that you look at that word total. Just state that the momentum before collision equals the momentum after collision in enclosed in an isolated system. So that second part, in an isolated system, is very important, but you must state that the total momentum before collision equals the total momentum. So you know, we are working with linear momentum, but collisions isn't just always in a linear way. So the basic principle is that you must take into account, even if there's a collision at an angle, that you take into account all the different components of the momentum before and the momentum after. Therefore, the word total is important in your definition. Now, then the next question after your definition is now applying that definition. And then you must work with a formula. And I've just indicated to you a few wrong applied formulas. Learners, in some way or other, learners have started to maybe correct word to get lost on really what this symbol, where this symbol comes from. So this is a wrong way of stating the principle of conservation of momentum. That is kind of like an E. It looks if it can refer to EMF even, and the confusion starts off with learners that get confused on the sigma sign used in the equation for the conservation of momentum. So please, that E before what does it mean? That E before. So you become lost with the sigma symbol, but then together with the sigma symbol, there must be, you must relate it at least to momentum. So please be on the lookout. Don't do that mistake in future, because it often occurs. Then the second problem, learners start off with this version of the conservation of momentum. So what's the problem here? The problem here is this learner don't indicate initial and final, or before collision and after collision. So this is an incomplete formula. At least we will take it as an incomplete formula. The principle is more or less indicated there, but you are going to lose a mark for that incomplete formula. So don't be sloppy on that. My suggestion therefore is, keep it simple. Start off with sigma, the sum of the momentum before or initially, equals the sum, sigma, of the momentum after or final. So then you know there's no way that you can get lost on subscripts like in this example, and you state the principle very, very clearly, and then you start off correctly, you get your 1 mark, and then the rest of the marks are then for substitutions. Remember, if the question is about the conservation of linear momentum or momentum in general, it's always about 2 objects. And I say it because later on, when questions are asked on impulse, then you are just working with one of the bodies being part of the collision. Right. Now, again, I just remind you, please don't use this formula for, and if I can go back, don't use this formula for a simple question on the conservation of momentum. So please, because what is the problem here? This is a wrong formula. The learner knows a little bit, but the crucial part, that negative, the change in B, is omitted, and then unfortunately it boils down to a wrong formula, and you then can get 0 for that question. Just a reminder, this is if you want to use this formula for the conservation of linear momentum, just use it correctly, but I will strongly recommend you to not go to this way of calculating conservation of momentum principle. Right, and I just remind you again, this relates directly from Newton's third law. Now, when dealing with impulse, you are only dealing with one of the objects in the collision. One of the collision. The change in momentum either of A or the change of the momentum of B. And then you know that is the formula that you use, the formula F net times the change in time times the time that the force acts on the body equals m, and then the change in velocity, so mv final minus v initial. You can just also, the formula for impulse, if you read it from this side, delta P equals mv final minus v initial, that is also a correct formula to calculate the impulse. That is for a special condition where the force is not given or the force is not asked. If the force is given or a force is asked, then you stick to this first way of stating it. If you don't ask, you can just either state delta P equals mv final minus mv idle. Remember, this is an impulse is one of the quantities where there isn't just one unit accepted, one SI unit accepted. So for impulse, that both Newton's second or kilogram meters per second, both are accepted units for impulse. So your final answer can have any one of these two units. Now, momentum and impulse are vectors, and therefore normally there's motion in 2 directions. A boy on a skateboard throwing away some parcel away from him, So the parcel is moving in one direction, and the reaction force on the buoy is on another direction, or a collision. There are two bodies moving toward each other and then collides and move in different directions. Anyway, you must look that momentum and impulse are vectors. You must choose a direction, for example, to the right as positive, and then you must award signs to the different values according to that chosen direction of you. If therefore the one object have a velocity to the left, then that velocity must have a negative value. And then, very important, if they just ask to calculate the momentum or the impulse, you must remember, again, it is vector quantities, so that there must be a direction attached to your final answer. If they maybe ask the magnitude of the momentum, then yes, it's not necessary for direction, but even, I will suggest even rather be safe than sorry. So normally attach a direction to your final answer for momentum or impulse. If you don't do it, unfortunately, you lose the mark for the final answer, although the magnitude of your answer is correct. Right. This is then a few comments then on momentum. Just moving on to the next topic, and then that is a topic on energy, work energy, and I think that will be the topic that maybe it will take quite a few minutes, and then the topic maybe that I will end off later on. I also have later on a November slot, and then we can try to finish off the other topics. Right, let us look now on work energy power and tips, and especially some common errors. I just want to remind you, starting off, the general definition of work done or energy transferred. You know, if you hear of the topic work energy, you immediately look at W net equals delta K, or WNC equals delta EP plus delta EK. And you forgot what in general work done is about. And in grade 9, you have been exposed to the principle that work done by a force is a product of the displacement of that object, and then, very important, and the force acting on the object in the direction of the displacement. And in grade 9, normally you don't have any angle between the displacement and the force, so it was a very simple calculation. But now, moving on, we are working with examples where the force and the direction of the displacement isn't the same. So this is the general formula for work done. The force times the displacement, delta x or delta y, and then this cos theta. And what's the purpose of this cos theta? The purpose of this cos theta is to make sure that you're only working with a component of the force in the direction of the motion. Right. Now, so this formula can be used to calculate the work done by any type of force. The work done by applied force, the work done by frictional force, the work done by gravitational force.